Hello everyone, welcome to day third of a very Leetcode challenge, and today's question is linked list cycle. In this question, you are given a linked list and you need to tell whether a cycle exists in that linked list or not. If it exists, you return true from it. If it doesn't, you return false from it. How do you interpret the input? The input is given as 320 minus 4, and the linked list is at the cycle is at the position 1. Also, you are not given this position value, it's just for your reference and pictorial representation. So please ignore that this value is given to you. As you can see, there is a cycle that exists in the linked list, and that starts at the first index. 0th is the head of the linked list, and since a cycle is there, you return true from it. Similarly, in this question, the linked list starts at 1, and then we have 2. From 2, the linked list points back to the first index. That means the cycle exists at the 0th position, and you return true from it. For this case, there is no cycle in the linked list, as indicated by the pause value, and there's only one node in the linked list, that is head. Since there is no cycle, we return false from it. So let's look at the algorithm that I have created for this. It's not a very tricky problem, it's a simple problem, and it requires, we'll be solving this by two approaches. One is the naive approach that usually comes up if you don't know about fast pointer and slow pointer approach, and that should be the way to go if you are unaware of fast pointer and slow pointer. If you are aware of it, you can directly jump onto the other part of the algorithm. So let's assume for a second that this question came in an interview and you are not aware of fast pointer, slow pointer approach. How will you go about it? The logic tells you to think about identification of duplication in a linked list. For checking duplication, which data structure is apt to be used? It's set, because if an element already exists in the set, and if you again see that element, you can identify that this element has been duplicated, and you return false from it, true from it, because that is the instance of a cycle. So let's walk through the algorithm. So you are given the linked list as this. This is the head of the linked list, and you check whether this node is there in the set or not. It is not there, move ahead, well and good. Add 1 into your set, then you got move ahead, then you get 2. 2 is not there in the in their set. Add 2 to your set, then move ahead. 3, add 3 to your set, move ahead. 4, 4 to your set, move ahead. 5, 5 to your set. And what is the next value in the linked list? The next node is 2. 2 already exists in your set data structure. That means it's a case of duplication. Duplication signifies uh, cycle, and since it's a cycle, you return false, return true. So this is how we will code the first approach. The time complexity of this approach would be order of n, the number of elements that are there in the linked list, and the space complexity would be again n, because every time you are seeing a new element, you are storing it in your set data structure. Therefore, both of them, the time complexity and space complexity, turns out to be equal to order of n. Let's I'll be coding this up in the coding section. Let's look at the other part of the problem. If the question said you don't have to use any extra space, how will we go about it? We will use fast pointer slow pointer technique algorithm. I have put in the descriptions and useful links for the slow pointer fast pointer algorithm. Please refer to those if you are unaware about this approach. I'll give you a high level view. How do we solve any linked list problem using, especially the cycle detection problem using slow pointer fast pointer approach. As the name says, there is a slow pointer and there is a fast pointer. Slow pointer is incremented by a value of 1. It simply moves to the next node, whereas fast pointer moves by 2 units. uh, one greater than that of the slow unit. So fast moves by two places and one moves by a single place. And that since the name suggests this, we will be doing exactly the same thing. So we have slow here, we have fast here. Till the time fast is not null, we will keep on doing the same thing, and we will move slow to one node ahead. Slow gets here, fast gets to the next place, fast to this place, and again let me change the color of pen. Again slow moves to the next place, so this slow gets here, and this time fast moves to two places ahead, this and this. So fast points to this place, and let's since both of them are not equal, and neither fast is not equal to the terminal state, we will again do this process. So a slow moves by one place, slow gets here, fast moves by two places. So first is this and then this. So here is fast, and let's change the color of the pen for the next iteration. And slow moves to the next place again. So slow points here, and this time fast also points to the same position. Since both of them turns out to be at the exactly the same position, that means there's a cycle in the graph, and we return true in that case. So that's the loop, a loop exiting statement. Whenever the fast pointer turns out to be equal to the slow pointer, you return true and exit from the loop. Otherwise, if there is no cycle in the graph, you would have terminated it by reaching the end of the linked list, and you must have witnessed the null node. If that is the case, you return false from your answer. So let's quickly code this up. Going in for the set approach first, and then followed by the fast pointer slow pointer approach, which is an efficient approach in terms of space complexity. So let's define a set of list nodes, and set equals to null. Set gets initialized to new hash set, and let's iterate through the linked list. List node it equals to head, while it is not equal to null. If we don't, if it, so this would be one terminal state for us when there is no cycle in the list. If set dot contains it, the current list node, you false, return true from it, because that's the case of cycle found. Otherwise, we'll add the current node into the set. If we are out of the loop by virtue of reaching the terminal state as null, you return false. And let's talk about the TC. TC is order of n. SC is again order of n. So let's try this up. Looks good. Oh, my foolishness. It equals to it dot next. My bad. Sorry. Accepted. Let's try the other approach. And let me just comment this. The fast pointer slow pointer approach, writing a safety case. If head equals to null or head dot next equals to null, return false. Otherwise, let's take two nodes. Fast equals to head, list node slow equals to head again. If fast dot next, fast is not equal to null, and fast dot next is not equal to null. So that's our terminal state when there is no cycle in the linked list. And what we will do, we'll move slow by 1 unit, we'll move fast by 2 units. If fast is not equal to null, fast equals to fast dot next, and for the case where slow turns out to be equal to fast, you return true. Otherwise, we are out of we have exhausted the complete list linked list, and we are out of the loop by virtue of these two, either of these two statements, and you return false. So typical way of writing the slow and fast pointer approach. Accepted. Time complexity for this would be order of n again, because you are visiting all the nodes once, at least once, and space complexity would be order of 1. Thanks for watching the video. Hope you enjoyed it.